And it's my pleasure to introduce Rachel Levanger from the University of Pennsylvania, who will be speaking to us today on a comparison framework for interleaved persistence modules. Thank you, Rachel.
Thank you, Henry. It's exciting to be here today. I do want to set the record straight, though, because I always forget to. It's Levanger is the last name.
Thank you.
Since this will be forever on the internet, love anger is how I
appreciate it.
No problem. And so, so here we are. We're talking about the comparison framework for interleaved persistence modules, and this is some pretty exciting work. Of course, I'm biased, but I'm hoping to give you a glimpse into the main ideas of this work. We're not going to get too far down into the details, but enough so that you get a sense for what's going on. First off, though, I'm going to start us off with the motivation and actually an application to studying dynamics with persistent homology. And this is actually the work that prompted us to undertake this theoretical study and extend some of the theory of persistent homology in order to handle a real-world problem here. So I know the video is a little bit choppy, but hopefully you can get a sense that on the top, we've got two different experimental two-dimensional fluid flows. So on the top left is a Kolmogorov-like flow. This is going to be mixing like you might see on the surface of a puddle of water, and there's oil on the top flowing around and mixing. And what you're studying there are going to be the vorticity fields, or how much magnitude of spin is happening at any point on the surface of the water. And then over on the right, you have Rayleigh-Benard convection. And this is the pattern that's formed if you have a very shallow layer of fluid that's being heated from below and cooled from above. And then these convection rolls start to form. And you see that the white bands, these are going to be the hot rising fluid. And then the dark bands are the cold falling fluid. And they're actually forming these beautiful spiral patterns. They call this spiral defect chaos because of the appearance of these beautiful spiral shapes in the patterns themselves. And so our goal is to develop tools that can study the experimental data, which means we may not have access to the underlying equations for the actual fluid flows, but we might have some numerical simulations or models. And we want to also develop these tools to be able to compare and contrast the differences between our models and the experiments. And we want to study both the dynamics of these flows and then also the patterns themselves. And so in essence, the study of systems like this is really the study of time-evolving scalar fields. So how is persistent homology going to help us with this? So here we have on the left an image of the vorticity field of Kolmogorov flow. So that was that video from the top left where you've got the mixing on the surface of the fluid. And here you have the actual vorticity. So positive direction is going to be spinning in the counterclockwise direction, and negative is going to be spinning in the clockwise direction. And so you've got these deep wells that are in black here are going to be clockwise spinning whirlpools, and then the white spots are going to be counterclockwise spinning whirlpools. Now, one thing I want to point out is this image has periodic boundary conditions. So the right and the left sides are identified, and the bottom and the top of the image are also identified. So this is actually fluid flow on a torus. Doesn't necessarily make a lot of sense for reality, but for the simulations, we don't want to worry so much about modeling the boundary conditions, and so it's very common to perform these numerical simulations with periodic boundary conditions. So in order to do persistent homology, we're going to use the method of sublevel set filtrations, and essentially we're going to take our vorticity field and we're going to threshold it from a low value up to a high value. And I'm going to hit play here. The persistence diagrams for dimension 0 and dimension 1, are then on the upper right. And they log the topological features of dimensions 0 and 1 that appear and disappear as you sweep through these sublevel sets. So here we can see at threshold negative 2.54, we've only surpassed 2 different local minima. And so these connected components are born at negative 2.5 approximately. Notice there's a whole bunch of other points here for dimension 0. These are going to represent the other 6 connected components or local minima that will pass here, leading up to -1.5 or so. Oops. So at this point, sorry, I'm not very good with this play button here. This up here. Here we go. So now you can see there are 8 local minima. Remember, this bottom one is identified on the left and right because we have periodic boundary conditions. And all 8 local minima are then reflected in these 8 persistence points in dimension 0. Now, eventually, these connected components are going to merge together when we pass saddle points. And you can think of persistence as pairing the local minima with the saddle points. Let me pause this again real quick. All of a sudden, 4 different components in dimension 1 have been born. And this is because once we pass through these different saddle points, these stripes now go all the way across the scalar field and wrap around that boundary. And so this creates 4 loops. You could kind of imagine if you had an inner tube or a torus, these loops might go around the width of the tube or the torus. And as we hit play, these saddle points will continue to merge in the vertical direction then, and we'll have 8 isolated local maxima corresponding to those 8 bright white points or the counterclockwise spinning whirlpools. And so you start to get a sense of how persistent homology can take your pattern, and especially through the relationship of the pairing of the critical cells, so the local minima with the saddle points encoded in the dimension 0 persistence diagram, and then the saddle points to the local maxima with dimension 1 persistence diagram, that you can then reduce this fairly high dimensional picture into a collection of points on the persistence plane. So we'll be using that to our advantage. The other sense of persistent homology that we're going to be using in our study of the dynamics of these fluid flows is persistent homology of a point cloud. So the way this is typically done is you've got your set over on the left, and you start inflating it by balls of radius epsilon. And when 2 balls intersect, you're going to draw the intersection graph and then look at the Viator's-Rips complex on that graph, or it's also called the flag complex. So let's start doing that. As our balls of radius r increase, eventually our isolated connected components will start merging. So edges start getting thrown in, and we can log that on our persistence diagram as a connected component that has died at this radius. At radius 0.5, a loop has been born, and so we're going to log that in our dimension 1 persistence diagram, and then additional components have died, so we're going to pass the death radius for our dimension 0 persistence diagram. And so we're going to end up being able to find loops or circular structures inside of point clouds. This is going to be relevant for studying, say, periodic or almost periodic flows in these fluid patterns. And so once you get to a much larger radius, especially once you surpass the radius of the point cloud itself, there's going to be no interesting higher dimensional structures in that point cloud anymore, and all of the interesting features will have died. Another thing we're going to be using and leveraging in our study is stability in the space of persistence diagrams. So by stability, we mean that from the space that we start from, whether it was a space of scalar fields or our point cloud on our Viator's-Rips complex, we're going to have a continuous map into the space of persistence diagrams. So as our space itself might be continuously time varying, we want to make sure that we're varying continuously in the space of persistence diagrams. So this metric that we're going to use is the bottleneck distance. The way it works is if you have 2 different persistence diagrams here, you're going to perform a matching of the points, so some sort of a bijection where you're allowed to match points to the diagonal, because as you can see, the blue persistence diagram and the black persistence diagram have a different number of points off the diagonal, so you can't have a bijection unless you include matchings along the diagonal. You're going to, for each matching, measure the maximum distance of 2 matched points in that function, and then take the infimum of that distance over all possible matchings, and that's your bottleneck distance. So this sort of tells you the bottleneck to having a close matching, or in some sense give you, what's the worst case scenario, the single largest difference in your persistence diagrams. Now, stability says that if I have 2 point clouds and their Hausdorff distance is bounded above by epsilon, meaning if I inflate my point cloud x by epsilon, I cover y, and if I inflate my point cloud y by epsilon, I cover x, then the bottleneck distance of my corresponding persistence diagrams is also bounded above by epsilon. So this can be useful, for instance, if you need to subsample a large point cloud, which we will have reason to do here in a few moments. And let's say you can only compute the persistence diagram for the subsampled point cloud because the other one was much too large. You want to know, using the bottleneck distance, where could the actual persistence point have been for my true point cloud? This is dimension 1 homology, so measuring this circle. And then how much noise might I have accidentally knocked out? So for instance, there's going to be very small circular features here in this sampling, but you're not going to see any of it with this sparser subsampling. So the true diagram might have had a point anywhere in this box. This is our bottleneck bound box, and then anywhere of radius 2 epsilon from the diagonal. So this, you can think of it as kind of creating a soup norm distance everywhere in the Euclidean plane. The same type of idea holds for real valued functions. So if you have 2 scalar fields, if their supremum norm is bounded above, or their distance, L infinity distance is bounded above by epsilon, so will their bottleneck distance of the corresponding persistence diagrams. So this is one of the videos I think that might be a little bit hard to track since we have the lag, but it actually ends up illustrating exactly the issue that we have to overcome with these dynamics. So this is an almost periodic orbit from a simulation of Rayleigh-Bénard convection flow. So on the left, top left, you can see this picture of these convection rolls, and at the middle, at some point that roll gets so thin that it pinches off and then moves to the outside. And compared to the slow pinching, that really slow squeezing, the pinching itself happens very quickly. So you really have 2 different time scales happening in these dynamics. Now, on the bottom left, you've got a bottleneck distance matrix between all of the pairwise bottleneck distances between the persistence diagrams that were taken at every single point in the time series. So we've sampled 500 frames of Rayleigh-Bénard convection. For each frame, generated persistence diagrams, and then taken the pairwise bottleneck distance for every single set of persistence diagrams in that set. So this is your—
And Rachel,
yeah.
Oh, I have a question. So the video on the top left, this is simulated data.
Yes.
And it's almost periodic. So it returns to a point that's almost the same as the start time. And then in your video, you're just replacing it with the start time. I can't even tell where that discontinuity is. And it's so close to being periodic that I can't even tell that you're just replaying the same video over and over again. Is that right?
Right, exactly.
Okay.
So what I have here is it's 2 periods. So you can tell in this bottleneck distance matrix, it's a checkerboard pattern that repeats itself 2 times in the horizontal direction and 2 times in the vertical direction. And so you can see that there's 2 different periods here. Another thing you can notice is that, so in the secondary block, there's a black stripe in the middle of the pattern. And once we get back to the primary block in the upper left, it's a white stripe in the middle of the pattern. So as far as the periodicity goes, we haven't talked about the speed profile in the bottom right. This is actually showing the actual values of the super diagonal of the distance matrix. So the black line is the bottleneck distance between consecutive frames. So if I want to know from one time point to the next, how much of my persistence diagrams changed in terms of bottleneck distance, that's what this black line is. And you can see that it's going along very smoothly, very slow changes, and then all of a sudden something drastic happens. And you have a very discontinuous jumpy speed profile. And this is essentially telling us that not only since you guys have lag in the video and can't resolve exactly how fast all those fast dynamics are happening, we haven't even sampled our system densely enough to resolve those really fast moving dynamics. And so this is a big issue when you're trying to do any type of numerical or dynamic analysis of these fluid flows that might have multiple time scales happening or events happening on multiple time scales, is how do you adequately sample both time scales? So just to further visualize what we're trying to do here is imagine we've got a single periodic loop that has slow moving dynamics across the top and the bottom, and then fast moving dynamics across the sides. So if you sample uniformly in time, you're going to get lots of samples across the slow moving dynamics, but all of a sudden when you go through the fast moving dynamics, you might only pick up a point or two, if any. And then once you're back on the slow dynamics, you'll pick up lots of points. And then again, you might not pick up anything in the fast moving dynamics. And so that's exactly what was going on. And we could see that as evidenced by the discontinuous bottleneck speed profile. So we want to make sure that we sample it densely enough. How can you get a sense for whether or not you have sampled it densely enough? You can actually look at the persistent homology of that. So we imagine then we have all of these scalar fields that we've sampled the trajectory from. We've now generated persistence diagrams from every single sample. We have a point cloud of persistence diagrams, and we use our bottleneck metric to look at it as a point cloud in a metric space. Then we do persistence on the point cloud of persistence diagrams to get a sense for what's going on with those dynamics in this more abstract space. And you can see if you look at the dimension 0 persistence diagram, it doesn't coalesce into a single dynamical structure until radius 20. But the diameter of the entire point cloud was radius 100 or so. So this is a pretty big gap in the trajectory. Notice also you do have the appearance of a loop once you get to that diameter 20. So once it coalesces into a single structure, you do see evidence of some sort of a periodic orbit or some circular structure. But it's hard to say if that might just be noise or an artifact, because you've really missed a lot of the trajectory. So what we ended up doing was we resampled the periodic orbit much faster and over more periods to close the gaps. But then we had 70,000 sample points. And I'm pretty sure even Gregory Henselman's Irene software and also Ripser, I don't know how they would do with 70,000 sample points, but I don't know if we're quite that good yet. So we needed some way to handle this. How are we going to, yeah.
And Rachel, this is 70,000 sample points. Those sample points are persistence diagrams.
Right. Originally they were scalar fields, right, but then we turned them into persistence diagrams. So 70,000 scalar fields become 70,000 persistence diagrams. Mm-hmm. But by the stability theorem, if we subsample the point cloud at a radius of 4.5 units in bottleneck distance, so this is about the width of a consecutive sample point if you look at the resolved dynamics, and then compute the approximate persistence diagram, this is the picture that we get. So we now have coalescence into a single dynamical structure at 4.5, and then we have the birth of a loop also at radius 4.5. So this is going to be your primary periodic orbit structure. And then there's actually a secondary loop structure happening here. So this indicates that the periodic orbit is probably twisted or folded or pinched in some way. But now we can actually say with confidence that these two loops actually would exist in the original point cloud because they are bounded away from the diagonal. Now you might be noticing, Rachel, why do you just have the gray boxes on the lower left corners of the persistence points and not all the way around like you told us you should have according to bottleneck distance? And this is exactly where this comparison framework theory comes in. So given only the classical stability theorem and that classical stability result, where you can look only at the difference in terms of the bottleneck distance between persistence diagrams, this work that we did extends that result to a much more general class of interleavings, and you can get more precise measurements on the errors that you might be introducing in your system by taking different types of approximations. So that's what I want to jump into now, is this comparison framework for interleaved persistence modules. And now we're going to change gears dramatically. So that's it for the motivation. Now let's get into the mathematics and see what's going on at the persistence module level to enable us to get a little tighter control on our approximations when we're doing applications. So by persistence module, we just need a real valued indexed family of finite dimensional persistence, vector spaces. And then you've got linear maps between the vector spaces when your index S is less than or equal to your index T. And you also make sure that when you compose them, you get what you should get. So if I have R less than or equal to S less than or equal to T, if I jump from R to S and then S to T, that's the same as jumping from R to T. So normally you start with a filtration of a topological space, and then you apply homology with field coefficients in some homological dimension n, and you end up with a sequence of vector spaces and linear maps. We're also going to pay attention to special persistence modules called interval persistence modules. I'm going to go through this a little quickly because I think most people who would watch this video would know this part, and if you don't, you're probably not going to learn too much from just the talk. So I'm just going to try and go through this a little quickly so we can get to the meat of the theorem. But you have these interval persistence modules that are essentially 0 up until you get to your field K, and then from then on you've got identity maps until you hit 0 again. And the structure theorem for pointwise finite dimensional persistence modules, so this is where every vector space has finite dimension, you can always break it up into a collection of these interval persistence modules such that your original persistence module is a direct sum or isomorphic to a direct sum of interval persistence modules. And these persistence modules made of the intervals are what form the barcode or the persistence diagram of the persistence module itself. Now we're going to be getting into interleavings, which is a way to compare how close two persistence modules might be to each other. I've always thought of it as a way also to sort of braid persistence modules together. So the idea is you're going to have two persistence module morphisms or maps from a persistence module V to persistence module W, and then from W back to V, such that just applying these maps as a regular persistence module morphism, these squares commute, but then also the triangles commute. So if I take the morphism from V to W and then apply the one from W to V immediately, it's the same as if I had just taken my transition map along V, and then same for W. So you want all of these shapes to commute. You might notice that I've put this in a pretty general framework. So instead of having jumps of, say, epsilon that you might be used to, instead we've got two monotone increasing functions, tau and sigma, that tell you how far in your indices you're going to jump when you go from the top down to the bottom and the bottom back up to the top. Now, for the applications, we're going to think of this as the persistence module along the top. That's the one that we can compute. So let's say this might be like the subsample of our large point cloud. And then W is the persistence module that we're unable to compute because it's either too large or experimentally inaccessible, something like that. Now, matchings are also going to be part of this language that we'll use. This is the same type of matching that you used in, say, the bottleneck distance. And the idea is matching between two sets is going to be some bijection between subsets of those sets. So think of the matched points that are off the diagonal. Those are actually in the matching. And then all of the unmatched points are the ones that were just sent to the diagonal. So here is, I guess, the first statement, or the easiest, simplest statement of the algebraic stability theorem for generalized interleavings. So if you have two pointwise finite dimensional persistence modules, and they're tau sigma interleaved, so remember tau and sigma tell you how much you need to jump when you go from the top module down to the bottom and from bottom to the top. And if these two maps are bijective, they don't have to be bijective. The theory does support translation maps that are not bijective, but it's much easier to state when they are bijective. Then for any points, yeah.
Oh, sorry. Were the transition maps, did you say monotonic though? So they could be sort of injective but not surjective?
That's right, exactly. So yeah, the translation maps, in full generality, all they have to be is monotonic. They also need to have the composition, tau and sigma composed tau, needs to be greater than or equal to the diagonal. So it always has to move you forward if you go down and then back up again, or up and then back down again.
If tau is not surjective, then it's also not continuous. Well,
and that's okay too.
Okay. Okay.
So in full generality, and we're actually going to see an example of one of these non-injective, non-surjective maps. It's actually going to be piecewise constant for discretization. And this enables you to then almost do a calculus, let's say, on how to compare the persistence modules that have been discretized or have gone through under other transformations.
I see. Cool. Very cool.
So it's pretty exciting. So imagine you've got a point from V that you can compute. So that's the point B comma D here. If it's matched, then we know that we can bound the location of B prime comma D prime by on the front. So the birth could be as far forward as tau of B, and the death can be as far up as tau of D. And then it can be bounded, it's going to be bounded below by sigma inverse of B and D. And so you can imagine, and this is actually directly generalizing, sort of going directly through the proof that Uli, Bauer, and Mike Lesnick gave for the induced matching theorem, but using these general interleavings instead. If you set tau and sigma to be T plus epsilon, you get exactly that epsilon box around the point that you get in the regular bottleneck distance stability theorem. But now you can control it with these monotone increasing functions. Let's see it in action. So here we're going to look at approximating the persistence diagram of a finite point cloud via subsampling. And this was our original example from the Rayleigh-Bernard convection, that periodic orbit. So let's say we've got a subsample of X, and we know that the Hausdorff distance of these two sets is bounded above by delta. Well, notice that X already covers Y. And so Y includes directly into X, but Y you might have to inflate by radius delta in order to cover X. So there's an asymmetry going on here that we're going to see pop out in these asymmetric interleaving equations. So we have this sort of a structure going on at the level of the RIPS complexes. So as we start to take our points, increase them by balls of radius epsilon, build the pairwise intersection graphs, and then take the flag complexes, we'll see that the RIPS complex at Y always includes down into the larger RIPS complex. And since we know that we only need to inflate X by, or Y by delta in order to cover X, that once we take our radius of T and add delta to it, we get a map actually from R back up to R of Y. This is not an inclusion map though, because the RIPS complex for Y is going to be much sparser in general. But we can use the nearest neighbor map. So for any point in X, I'm just going to map it to its closest point in Y. And it turns out that this is a simplicial map, and it's simplicially homotopic to the inclusion map. And you can prove this. It's just basically a consequence of the triangle inequality. So this means once you apply homology, the homology functor, you're going to end up with a commutative diagram at the top at the level of vector spaces and linear maps. So then you'll have your commutative squares, and you'll have two commutative triangles. And so you're going to have an interleaving at the level of the homology vector spaces with your tau translation map. So this is the one going from top to the bottom, is the identity. So those indices don't change. And then the sigma translation map, in order to go from bottom to the top, you have to advance in index up by delta. So sigma is going to be t plus delta. So if we go through and apply this then through our the algebraic stability theorem for generalized interleavings, this tells us exactly, well, I can take the inverse of sigma, which was t plus delta, and it's just t minus delta, and that's going to be the lower bound then for my match points. And then the upper bound is just actually the original point itself. So that's how you end up with this left-hand lower box in the diagram, and this is also why you don't have a 2 epsilon or 2 delta band along the diagonal. You have a single epsilon. And let me go back to the original statement. I didn't point this out, but any points matched to the diagonal or unmatched, they're going to have a sigma composed tau of B, and tau composed sigma of B prime is going to be an upper bound for the depth. So if the bars or the persistence points are closer to the diagonal than sigma composed tau or tau composed sigma, that's going to mean they're not matched. And in the case where tau and sigma were both t plus epsilon, that then becomes t plus 2 epsilon. So that's where the 2 epsilon really comes from along your diagonal. So that was pretty exciting. Let's actually dive in now another layer deeper and see what's going on at the level of the algebra. This is just a very quick proof sketch to give you an idea, and also because I don't know if it gets enough attention, it's going to go through in very much detail how the induced matching theorem for persistence modules works. I think that's very important work in this field, and so I always enjoy the chance to go over exactly how the induced matching theorem of Bauer and Lesnick works, because it's really neat that it works out, and I think it's a really great tool to have and to understand when you're working in persistence module theory. So I want to take the time to go through this. Plus we use it, it's kind of the key and the pin to unlock all of this theory. So say we have our persistence module V. This is the one that we can compute. And let's see, I can't see what that says up there. Oh yeah, so we can turn that into a direct sum of interval persistence modules up here. So we've got our barcode decomposition of V up at the top. And then let's pretend like V is just a single interval for now to simplify things. And say we've got another persistence module W that we can't compute. And we've got some persistence module morphism between them. So F is going to map pointwise in the index vector spaces in V to vector spaces in W. And we always know that the squares are going to commute. So if we go over and down, that's the same as going down and then over by the same amount. So we might have some bar down here in W, say it's also just a single interval. We know by commutativity that this bar has to actually be back and to the left of the original bar we started with. And that's because if it was to the right, I could go down and then over and still be non-zero, but if I go over and then down, it would be 0. So this is a fundamental constraint that I think is important to observe with these persistence modules, is if you have a persistence module morphism to one to the other, then these bars that they get mapped to kind of sit down and to the left. Now the question is, how are we going to match these bars? So you can always factor a map through its image. So here we've got the image of the map, and that's going to be, you now have an onto morphism from V to the image of F, and then an injective morphism from the image of F into W. And we want to know, how do these all correspond? Notice that the left-hand endpoints here match up, and then the right-hand endpoints also have to match up here. And this is sort of a hint at how it all ends up working behind the scenes, although I'm not going to get into those details exactly. So how does the matching work? We also want to keep track of, these differences in lengths here. So we may have matched this blue bar to the yellow bar, but this kernel hangs out here on the end. And we might have matched this yellow bar into the red bar, but then the co-kernel hangs out there on the end on the left as well. So keep in mind this sort of wiggle room that we're allowing ourselves when we're matching. So now let's put all of our other bars back up there in V. The way this matching algorithm goes is you first isolate all the bars that have a particular birth time. So this algorithm proceeds birth time by birth time in your persistence module. So we line them up and we look at all the corresponding barcodes in the image of F that have that same birth time. So maybe this one was mapped to 0 for whatever reason, or who knows what might be happening here. We've got these two bars that are matched up, and we're going to match them greedily now by length. So the longest bars in the blue set are going to be matched to the longest bars in the yellow set. And this can always be done for a theorem in the Bauer and Lesnick paper. And then you're going to line up the death times from W with death times in the image and do the same thing and do another greedy matching. And so in this case, you're going to have this top bar gets mapped to the longest bar through the image and then down to the longest bar in W. So you'll get this bar at the very top and this bar at the top on the bottom are matched. And then maybe this one is matched with another one down here. So this is how the induced matching theorem algorithm works. So this is a way that you kind of get around some of the problems in multi-parameter persistence, is by actually letting go of the algebra for just a minute, passing to a combinatorial algorithmic approach. But what's really amazing is the theorem that they prove is as long as there's a morphism from V down to W, this matching scheme always works, and every single bar that was in the image is matched. What about the unmatched bars? So how do we deal with that? And these are all going to be all of our bars that go to the diagonal. Well, remember the length of our kernels and our co-kernels. We want some way mathematically to talk about the sizes of these bars. This is done through this idea of being epsilon trivial, or for our general case, if you have a monotone map that's bounded below by the diagonal, you can call any persistence module sigma trivial. If I advance by sigma t from t, I'm going to end up with 0 for every t. So if sigma was just t plus epsilon, that means every bar in my persistence module has a length shorter than epsilon, if it's epsilon trivial. But now you might have, not just a t plus epsilon as your translation map. It can have variable length all along the real line, and you've got a little bit tighter control on these bars. The non-uniform induced matching theorem, so if you go through and extend Bauer and Lesnick's work with these general translation maps, it turns out that in this induced matching theorem, if sigma of b, so if you move the birth time of the bar up by sigma, and if that doesn't quite reach the death time, that bar is matched. Actually, that starts up here in the top. And then if it is matched, then b prime, so the bar down at the bottom, it's bounded above by the original birth time and below by sigma inverse. So there's only a single translation map actually that's used when you apply the induced matching theorem. And so you have to actually go another step. And this is also what they do in the induced matching theorem paper if you have a full interleaving. So let's say we have a tau sigma interleaving. So this means we can start at index t up in the top. advance forward by tau, and then advance forward by sigma again, and we get this triangle. We have our interleaving maps, phi and psi. Also notice, so let's see, this is something that makes it so algebraically how this works out. You can think of having an operator on the space of persistence modules, or this functor that's, you could say it's a translation functor or translation map between persistence modules. And it's going to take W, and instead of having the actual vector space at index t at time t, we're going to replace it with tau of t. So you can imagine taking your persistence module W and shifting it back by tau inverse, and that's what this translation functor does. So the reason we have to do this is, for an honest-to-goodness persistence module morphism, you have to have a map from index t in the top to index t in the bottom. You can't actually skip forward. So what they do is you apply the shift first, so then you're going straight up and down, and then you have to kind of shift it back later on. So that's the reason we have these translation maps. So how does the proof go through then? Let's say we have these two interleaved persistence modules, and to stay in the simple case, let's say that the translation maps are bijective. So we take one of these interleaving morphisms, it goes from V to the shifted persistence module W straight down. There's a lemma that you can prove that says if you have two persistence modules that are tau sigma interleaved, and you take an interleaving morphism, then both the kernel and the co-kernel of that morphism are sigma composed tau trivial. So the parts that aren't mapped, you know, they're in the kernel of the morphism or they're co-kernel of the morphism. If they're both really short, then a direct application of the non-uniform induced matching theorem says that if we control the sizes of the kernels and co-kernels, we can control the type of matching that you get out of it. So now we have a matching that we can build between V and the shifted persistence module W. We just unshift it now with the inverse of tau to get back to W. And when you apply this tau inverse, you end up with the nice version of the algebraic stability theorem for these generalized interleavings. And so originally, you might have only seen the induced matching theorem applied with sigma composed tau, but if you put this tau inverse in there to shift everything back, all of the mass cancels out very nicely, and you end up with this very simple relationship then, with sigma inverse and tau controlling the birth and death times, and then the two compositions in each order controlling the points along the diagonal that are unmatched. So that's kind of the nuts and bolts of how it works. Let's look at a couple more applications for fun. So first of all, let's look at if we have one of our scalar fields. So in the real world, I don't know what your position on physics is, but let's say that our real experiments here are actually continuous smooth functions, or maybe they at least are mathematically in our models. But once we put them in a computer, we have to discretize them and turn them into images. So let's say we do that very cheaply in the range, discretize the range just by taking the floor function, let's say. So now we're going to have our sublevel set filtration of our domain from our actual function f, and then our approximation filtration coming from this discretized range, our approximation module y, or filtration y. And we can get this sort of interleaving at the level of the topology of the sublevel sets. So you have inclusion going across the top. Y0 up to Y1 is actually constant because no values are changing in H if you're not at an integer value. And so once you pass X0, now these are actually equal, once you pass X0, you have to include up to the next index to make sure you've dropped enough values into your sublevel set. So here's our structure we get at the level of topology in order to include. When you apply homology, then you can look at what your translation maps might be. This is a right continuous version. It actually doesn't end up having to be right continuous, but this was a little older version of the slide. But you've got these interleaved persistence modules now, and you can now just take these functions, compute the generalized inverse of this discontinuous map sigma, and actually get this picture out that gives you a much more precise view of how your discretization might be affecting your persistence module. So here we've pretended like we had some sort of a scalar field we were truncating, but you can also imagine if you started with any continuous persistence module and then just sampled it integer values, this is going to be your discretized persistence module. So any point from the discretization could have actually come from a real point anywhere in this lower left-hand corner. And then we might have wiped out any small features in these purple or blue regions. And it's actually possible that we might have introduced some points off of the diagonal. So let's say you had an ephemeral persistence module, meaning it had a non-zero vector space at only a particular point. If we're using that floor function, we'll see it at an integer value, but then it won't disappear until the next integer. So if you have a non-constructible ephemeral persistence module, you can actually accidentally lift points off the diagonal, and they never would have been seen in the original persistence module.
And Rachel, so here you're tracking the in your sigma and tau and sigma inverse tau inverse, you're tracking both the unmatched points from one diagram and for the other diagram.
Exactly.
That's
nice. So that's the blue and the pink. So we didn't actually compute any of those, but if they had been, any unmatched points would appear in these two regions. Now, that's not quite how it goes for an actual digital image. For a digital image, you don't even have a smooth domain. You might have some cubical complex approximation of the domain. So you need to do first some sort of simplicial approximation of your function f with a function g. Let's say you can do that to within some epsilon guarantee, and then you have to take the floor of the range to discretize it. How do these two approximations then chain together to affect your final outcome? It turns out there's a theorem, and this is in Bubinic, Da Silva, and Scott's 2015 paper, maybe 14, on their generalized interleavings, that you have this sort of triangle inequality or composition of interleavings. So if you have a tau sigma interleaving that's then followed up by a rho eta interleaving, you can actually go down 2 steps by tau and then rho, and then back up eta and sigma to get a larger interleaving from the top to the bottom. And so we can chain these 2 steps of approximation together, compute what was tau and sigma, what's rho and eta, and then just use essentially this calculus to combine them and compute what the exact interleaving is going to be. And the picture then that comes out from this 2-step approximation looks more like this. So you can see where this little bit of epsilon has crept in and exactly how it's affected your final approximation. And some of it you can kind of predict, but I was surprised myself when I did the computations that this is exactly what it looked like. It was hard for me to imagine in my mind exactly how it would be affected. And so you can see you still have quite a bit of difference between just the worst case scenario bottleneck distance bounds and then the actual bounds that are given by a tightest possible interleaving. I think we have time for maybe 1 or 2 more examples.
Yep, definitely.
Okay, great. So one thing we've included in the paper is we've gone through some of the existing approximations to point clouds that exist in the literature. So point clouds in Rn, and then point clouds in arbitrary metric spaces. So it's quite common in general, let's say you start with the check filtration of a point cloud, because the NUR, if you take the check complex of your balls of radius epsilon around your set, you're actually going to get the true homology in certain cases, but that's very complicated to compute, and so people pass to the Vietoris-Rips complex instead. Well, you can actually look at the tau sigma interleaving between these 2 complexes. Notice sigma is just going to be T itself because the check always includes into the RIPS complex. And so you don't have to change your index in order to get that inclusion. But in order to go from RIPS into check, you've got to inflate your radius by some amount. And then let's say you want to do a two-step approximation. So going from check to via torus RIPS, and then from, say, via torus RIPS to the sparsified via torus RIPS complex, you would then just compose these maps per the triangle inequality, and you'd get a full computation of your approximation that you might want to use. Another application we have in the paper that's on arXiv is, what if you have a sequence of via torus RIPS filtrations from a cover tree? So by a cover tree, I mean maybe you've got some very dense point cloud here at the bottom. And if you do your via torus RIPS filtration and apply homology, you'll get one persistence module. And this is going to be the true persistence module. But say it's very large, and so you run out of memory very quick when you're trying to compute this thing because the number of simplices is just overwhelming. So you can subsample at some radius and say, well, I'm going to choose some representative subsample such that when I inflate it by a ball of this small radius, I cover the previous subsample or the previous set. And now I can look at a first approximation persistence module from this subsample. I can play the game again, inflate it by a larger radius, and then take a representative subsample from that set, apply homology to that second level approximation, and I end up with this sequence of persistence modules at coarser and coarser resolutions sampled from my point cloud. And so one of the questions that we address is there a way, and it turns out there is a way, to start at this very lower level, go along your RIPS complex, hand off to a sparser RIPS complex via a simplicial map, continue along for a direction, hand off again, and sort of weave your way up this sequence and keep track of what's happened. So the technique we use to combine these persistence modules is a stitching or splicing technique. So let's say you've got V and W are tau sigma interleaved. So remember, V is the one you can compute, W is the one you can't compute. And then you've got some other approximation of W, and it's tau prime sigma prime interleaved. You want to know, how can I splice V and V prime together to get a spliced up approximation of W? And essentially what you can do is use these interleaving maps themselves to create that splicing map that goes across the top. So from the left side over to the point T naught, your original persistence module V, you jump down to W to tau of T naught, back up to V prime, and then you continue on the V prime track. Now, if you want to keep track of what's actually happening with your interleaves and prove that this is still a persistence module, you have to do a little bit of work. But there is a formula. You can write it down. It's kind of a pain, but if your maps are nice enough, it's not that big of a deal. In order to prove that you still have persistence modules and you still have these interleavings, you have to address those commutative squares and triangles from the interleavings. And so those end up giving you the following 5 or 6, I think, commutative diagrams. So you can see, here's your problem spot. And I have to show, if I started at S and go to T, here's a commutative square. Does it actually commute? Likewise, if I started at S on the bottom and went forward to T, does it commute, when I go forward? And you have to address all these situations where you might have landed on that square in the middle where the stitching happened, or whether you mapped past it. And it's pretty straightforward exercise, but I thought there were some cool diagrams that came out of it, so I wanted to show you all. But it does go through and it does work. And this is the type of persistence diagram that you get then. So from the stitched persistence module, you maybe computed these 3 points, and the regime that your birth or the death time is in, depending on if you're in the fine sample or the coarse sample, will then change accordingly. They're all subsamples, and so your estimates are always going to drop down to the lower left, just like they did for the regular subsamples. And then you've got a little bit of extra wiggle room during that stitch, that jump that it had to do from the point T naught to, I think it would have been sigma and then tau prime when it jumped back down and up. The very last application I have, this will just take a second, is persistent homology under non-uniform error. So typically when we do persistence, we think of having a straight line and doing sublevel sets according to the straight line. So as soon as my function drops below the straight line, I log a birth of a component and then my death, but I can actually put some sort of a wiggle or distortion around my uniform persistence line and create non-uniform filtration. So if I perturb my straight line by some, say, the sine function, I'm going to put a whole bunch of artifacts into my persistence diagram. And one of the questions in this paper was, how do the two persistence diagrams relate? And you can partially answer this question through this theory. So if you play the same game and figure out how do I construct my interleavings, we won't go through all these details, then essentially what you can figure out is that tau is going to be t divided by alpha, where alpha is the infimum of that perturbation function that you started with. In our case, it was 0.25 times the sine function. So contract the sine function, then move it up a little ways. And then sigma is going to be the supremum of that function. So what was your sort of minimum perturbation and what was your maximum perturbation? And then you can actually run these equations through and get exact error bounds now. So you can see the two persistence points at infinity more or less coincide because even the uniform and the non-uniform, they touch this local minimum at about the same time. And then this black point actually gets associated to the point in this box here, and these other three fall under the noise that was, say, introduced by distortions. So I know that last part was a little quick, but hopefully it gives the idea of some of the utility of this framework. You can see our work has been posted on arXiv recently, finally. So all of the guts and glory are in the paper on arXiv. And I think we're just about out of time. So thank you all for listening. Here's a commutative diagram. Thanks for having me.
Thank you very much, Rachel. That was a fantastic talk. So there was a question that Barbara Giunti chatted in. I think this was a couple slides back, probably on the slide about check and RIPS complexes and Euclidean space and for arbitrary metric spaces. So let me ask that first before I open it up for further questions. So Barbara's questions reads, in Rn, Euclidean space, check and Viator's RIPS should have the same time complexity?
Oh.
So this might be time complexity of computing one versus computing the other?
Yeah, in Rn, they might. I don't get too much into the nitty-gritties of all the computations, so if that's the case now, then that's awesome. So if you're lucky enough to be in Rn, then that's awesome. So in the application we talked about with the dynamics, we are unfortunately in the space of persistence diagrams. So we were not in a metric space in Rn. I don't even know if the Nerf theorem necessarily applies, but we are definitely down at this other level here, where a check filtration in the space of persistence diagrams would be very, very difficult to compute.
I guess I'd also be interested in knowing more about that question. I would have guessed that the complexity of check increases, gets worse and worse as n goes up. But if somebody wants to fill me in on more on that question, I'd be interested in it. Other questions for Rachel?
I guess one more thing. I know that in Hare and Adelsbrunner's book, they do address the check complex, and it has something to do with this mini ball computation, and it looked very complicated to me. So I'd be surprised if we are to the point where they were the same time complexity. But if we are, if somebody's come up with an algorithm, that's pretty cool.
I think it's because in Rn you can compute means, so you can compute the center.
Cool.
Yeah.
Other questions for Rachel?
Even if also, no, I guess that wouldn't count, because even if the time complexity was the same, I guess check would be sparser than RIPS, so that might actually be easier from a persistence standpoint. But I leave those to the experts.
Further questions for Rachel? Let me ask you a question. So in some of your first examples, you had scalar fields potentially on a 2D domain. You were looking at periodic boundary conditions, say a torus, but pretend it was just maybe a disk or square. So there's some duality type theorems, or even in 3D, where you can, well, let's talk about the disk. You can sort of read off things about the one-dimensional persistent homology from the zero-dimensional persistent homology and vice versa. So I'm curious, have you looked into, does that play nicely with your approximation bounds? So when you have this duality between different dimensions, I would suspect that it just sort of fits into your framework, and that if you compute these, you have these blue boxes versus these gray boxes. I would guess those would all, there's some duality that happens for those boxes as well, and it all matches up perfectly, so that you don't really gain much by starting in 0 dimensions, transitioning to 1 dimensions, and then using duality to get it back. I would guess that there's nothing to be gained by that, but maybe.
Yeah, the gain would have to be in some sort of asymmetric interleaving, when you compare the sublevel set interleaving with the superlevel set interleavings.
Right.
So the duality I think you're talking about is maybe the Alexander duality.
Sure. Yep.
Where you've got, say, persistent homology on a sphere, and then the sublevel set would be the complement to the superlevel set, and then that would be the complement on the sphere. So you do get that duality, but in order to get some sort of a gain, you'd have to somehow, where the sublevel had a good interleaving, the superlevel might be bad, and then where the superlevel was bad, the sublevel would have to be good in order to actually get anything out of it. And I don't know for sure how that type of asymmetric sub versus superlevel interleaving would go. I've never thought about that. That's kind of cool to think about.
So Liz, go ahead.
No, that's it. Go ahead.
Liz Munch from Michigan State typed in a question. I'm reading it. So, can you speak to the coefficient of T difference between the Viator strips and check complexes in Euclidean versus arbitrary metric spaces? Okay, and then she follows up. She says, "Where does the 2 come from? I would have expected this to have something to do with curvature or something like that."
I believe the 2 is just like a triangle inequality argument. And for some reason now, this says square root of 2. Oh, for Euclidean space, yeah. So as n goes to infinity, this turns into the square root of 2. But I want to say this is just a triangle inequality argument. For curvature, I mean, you'd have to have a space where you can even talk about curvature. And so say in the space of persistence diagrams, I think all bets are off. So I think 2 is sort of your worst case. I'm definitely not, I don't do a lot with geometry. So a lot of these technical questions about the nuances of the different spaces, I think there are definitely other people who can address those. But if you do know exactly what you can leverage, you can now put it into this wonderful interleaving framework and keep track of exactly your errors that you might introduce in your computations depending on the exact space that you're working with. So that's the idea.
Yeah, Liz responds, okay, I'm overcomplicating, thanks. But yeah, Rachel, your balances look exactly right there. In Euclidean space, you can only do square root of 2. You can do better if n smaller, but then in arbitrary metric space, you can only do 2. You can't do square root of 2. Further questions for Rachel?
I guess one thing I might also point out is what I found really interesting and surprising is I didn't go through and cherry pick approximations that would have asymmetric interleavings. Every single one of them that I found had an asymmetrical interleaving with tau and sigma. And so the tau translation map is different than the sigma translation map. But if you go through the papers, they're all stated with symmetric interleavings being the worst case interleaving. So I thought that was really interesting.
All right, well, thank you very much, Rachel, for a fantastic talk. And thanks to all of our audience members for joining in.